Okay, I will ask you some question. You just answer me. Okay. So, yeah, if I'm audible, then you will raise your hand. Okay. I am audible
Yes,
to
sir.
you.
So 1 second, sir.
Raise your hand.
Drawing that it's unstable.
Am I audible
So
to
now
you?
you're, so yes, sir, now you're audible, sir.
Okay. Okay, just a minute. Am I audible to you now?
Yes, sir.
Am I audible?
There, yes, sir.
Okay.
Sir, am I audible?
Yeah, so I was just checking whether my microphone is working or like through which medium the sound is going to you. Okay.
Okay.
So in the last lecture, what we did?
So we started with. So we started with the force acting.
Yeah. Let me just check. Okay, we're done with the solenoid and toroid. Yeah. Okay, fine.
Yes, sir.
Okay, yeah, correct. So we started with the force on a moving charge particle, right?
Yes, sir.
So in vector form, we write force on a moving charge particle as a charge of the particle into V cross B in scalar form, or you can say in magnitude. We can write as Q V B sin theta, correct?
Yes.
So basically, when a magnetic field will start applying force on you, so the other perspective is like this. So let's say in space, this is the magnetic field direction, and this field is developed by some other moving charge or some other current carrying wires. So this is already given to us. And the source which is creating is not known to us, but what we know is only the field. Now, if a charge will decide to move in the space, and let's say the angle made by the velocity vector with respect to the b direction is theta, then the magnetic force will act on the particle because it is intercepting the magnetic field lines. So the velocity will have two components, one parallel to the field lines, which is called v cos theta. Another is v sin theta. Okay. And the whole idea is that the rate at which you intercept the field lines will be giving you a proportional value of force acting on the charge particle. So when you move parallel to the field lines, let's say if it is v cos theta, then you will not experience any magnetic force. Understood?
Yes.
So you will not experience any magnetic force if you move parallel to the B vector. So you can see clearly the V cos theta will create nothing. There is no effect of V cos theta, but V sin theta is intercepting, or you can say kind of cutting the lines of force or intercepting the lines of force. And whenever you intercept the lines of force, then you experience the force. Okay. Is this clear?
Yes, sir.
Just okay. So V cos theta and V sin theta are the two components, and what we have realized that V cos theta is not responsible for the force that the charge will experience. It is a V sin theta which will let you experience the force. And what really matters is the rate at which you cut the force, I mean field lines. And therefore, the force that you will experience is going to be proportional to V sin theta, like the rate at which you intercept. It is going to be proportional to the density of field lines. Like if we have closer field lines, if I draw more of the field lines here, then you will end up intercepting more and more field lines, isn't it?
Yes.
So the B, when we say B is larger, it means sorry. So when we say B is larger, it means the field density is very high in the given space, and if the field density is high, then definitely the force is going to be bigger. And of course, it will depend on the charge, the magnitude of charge itself. So combining these three together, we can say that the force is going to be proportional to QV sin theta, and therefore we can attach some constant into QVB sin theta, and therefore in SI we take k equals to 1, which implies the magnetic force is QVB sin theta. Okay. All right. Okay. So now this becomes the formula, and we need to understand how to interpret the formula. So what really matters is that the charge must be intercepting the field lines, and if it is not intercepting, we say there is no. So imagine if you have infinitely large, infinitely long straight conductor carrying some current, and a charge particle is orbiting the wire in a circular path. What do you expect? Will it experience any force?
So when a charge particle is moving in a circular path,
Hmm.
where exactly, so? I mean, how exactly?
Okay. Around
Like
a wire.
around a wire.
Yeah, infinite wire.
Okay, sir. Sir, like if it is moving around the wire means no, this thing, sir. It won't experience any force.
Correct. Because the
It's
B
moving
will be
along
parallel.
the,
Yeah.
yes, sir.
So at any instant, the velocity vector will be parallel to the V vector.
Yes, sir.
So both will have same direction, so it will experience nothing. So there must be some other force which is acting there, which is creating this circular motion, which is not given to us. Okay. So yeah, it is possible that it may be a gravitational force. I mean, of course, we cannot say anything. So what we can say is that there must be some force other than magnetic force, which is making this circular motion possible. Okay.
Yes, sir.
So what we have to study is three things. First, motion in uniform and transverse magnetic field. Second is motion non-uniform and transverse magnetic field. Third is motion in uniform and non-transverse field. Fourth is okay. So fourth we can call motion in parallel electric and magnetic field. The last is motion in transverse electromagnetic field. And of course, there may be or there must be some other method, but what we are really interested is in these five variety of field. And under every topic, we have multiple conditions or scenarios that we'll see or explore one by one. So imagine, okay, we'll take the first case. The first case is motion under the uniform and transverse field. So motion in uniform and transverse magnetic field. So imagine if you have a okay, now we have multiple case when field is spread up to infinity. So which means field is everywhere. So wherever the charge particle will go, the field will be available. So what you do is you simply project a charge particle with some initial velocity. And V is the charge particle. Okay. Now, if you apply the magnetic force formula, which says that F equals to Q into V cross B, so we can clearly see that the B is into the plane, and the velocity is in this plane.
So force will be upwards.
So force will be upward, which is again into the plane of the V, right? So directional force will be in the same plane, right? This blackboard.
Yes, sir.
So force is still perpendicular to the magnetic field and velocity. And because force is having no component along the velocity, what will change? Magnitude or direction, or both? This force is capable of changing what? Only magnitude, only direction, or both?
Um, Sir, it will be changing the direction of the particle, obviously, but yes, sir, the magnitude, I know, sir, it won't be changing the magnitude at all.
Yeah, because there is no tangential component.
Yes, sir.
So to change the magnitude, we need some tangential component, which is totally absent here, right?
Yes, sir.
So because the force is upwards, it will try to bend like this. But at this point, when the velocity vector is like this, the force will again change the direction. It will be again perpendicular.
Yes, sir.
So it will keep on changing, but the direction of force will remain perpendicular. And therefore, the only possible path here is because the force is constant. So if we have a constant force acting always right angle to the velocity, the path is going to be circular. So eventually, the path that this particle will traverse is a circular path. And it will have a finite radius. And the magnetic force will act as the centripetal force. Okay. So here we can say magnetic force will act as centripetal force. Okay.
Yes, sir.
So because it's a circular motion of finite radius, we can find the radius by using the formula. So net force towards the center equals to mass into centripetal acceleration. And therefore, the only force acting here is toward the center is magnetic force, which is Q into V cross B. And here, because everything is mutually perpendicular, so it will simply become QVB, correct?
Yes, sir.
And that is the benefit of transverse field. When the field is transverse, then the formula becomes QVB. And because B is constant, so the entire term is constant.
Yes, sir.
And this we can attach mv square by r.
Yes, sir.
So the radius that it will traverse, the circle, the radius of the circle that it will traverse, we can write as mv by q into b, right? That's very simple.
Yes, sir.
Okay, so once we have the radius, it can be written in multiple ways because mass into velocity is called momentum, so we can write as p by qb. But a momentum and kinetic energy, we have the relation p square by 2m equals to ke. Therefore, p equals to 2m ke, 2m, just a 2m k, it looks better. So the radius we can also write in terms of now the last form of writing is like when a charged particle is accelerated through the potential difference of v. So let's say we have a charged particle which is this is plus, this is minus, so it will accelerate from here to here, and let's say from here it comes out. So when a charged particle will accelerate through a potential of v, then its kinetic energy you can write as the kinetic energy of a charged particle will be how much? Q into v. Okay. So the radius we can rewrite as, let's say this particle enters the transverse field. Okay. So we
I
accelerate.
don't exactly understand.
Pardon?
Sir, I don't exactly understand the last part, sir.
Okay, if a charged particle will accelerate through the potential difference v, what will be its kinetic energy?
So that would be QV, but it's not. But here it is moving with constant velocity.
Yeah. So now with see you accelerate and then you enter some field. That's the idea.
Okay, sir. Yes, sir.
Like first you accelerate for some time, and once you attain the velocity, you come out of this plate. Let's say this is the some parallel plate capacitor, and once you accelerate, you come out of this, and then you enter a field. Or you can say the moment you come out from here with some velocity v, I give you some or I switch on some magnetic field. That's the idea. So what will happen to the radius of such particle which has been accelerated through a potential difference of v volt is starting from rest? So your kinetic energy will be q into v, which means this is the energy which will gain. Okay, and now with this velocity or with this kinetic energy, you enter the magnetic field. Imagine that way. Okay. I think this is still not clear, right? Okay, no problem.
Sir, no, sir, I like understood the picture.
No, it's still like not a exact picture. It's like if I have given that kinetic energy through the acceleration mechanism before it made its way into the magnetic field region, or I have first accelerated the particle and then I switched on the magnetic field. Okay, there are many ways in which I can achieve this.
Yes.
So technically, it is done like this. But this is not infinite field. This is semi-infinite field. And imagine we have a box. Like this. Then the radius of curvature we can find in that case. So if you accelerate through this, then while entering this field, what is your kinetic energy here? So this is what I'm trying to say. Okay.
Yes.
So the radius can be written in multiple ways. One is mv by qb, p by qb, 2mk by qb, 2mqv by qb, which you can rewrite as 2mv by qb square. If you take the root for the entire thing. Okay.
Yes, sir.
So these are the possible ways of writing the radius, and why we are writing in these possible ways, because generally you will come across question in which you need to compare the radii of two situation. So they will tell you, okay, find the radius if they are given same velocity. So if two charge particle will have same velocity, then the radius will be proportional to mass and inversely proportional to charge, right?
Yes, sir.
So let's put a heading. Comparison of radius of two charge particles. So comparison of radius of two charge particle. So we can say R1. Okay. Okay. We'll take the case one. If both charge particles are given same velocity. So if V is same, then we have to use this formula, right? The first formula.
Yes, sir.
So R1 by R2 will be how much? M1 by M2 into Q2 by Q1 by, because B is same for all, right?
Yes, sir.
So the ratio of radii will be the ratio of mass into the inverse ratio of charge. Right? This is the how we can get the answer. Okay.
Yes, sir.
So here V is constant, right?
Yes, sir.
We can take the case 2. if momentum is same for both particles. In such case, we have to take the formula R equals to P by M QB to compare. And because momentum is constant and B is anyway constant, we can say R1 by R2 will be simply inverse ratio of charge, right? It is clear?
Yes, sir.
If Ke is constant, is same for both particles. Right?
Yes, sir.
Okay.
Yes, sir.
Case 4 we can say as if both particles has been accelerated through same potential. So we have to use the formula 2m. So R will be proportional to, because V is same, B is same, 2 is constant. So we can write like this. Okay. This clear?
Yes, sir.
Okay. Okay. So the next thing is like if we have infinitely spread magnetic field. So we have realized that the particle will perform the circular motion, right?
Yes, sir.
The question is how much time it will take. So what is the time period it will take?
Sir, 2 pi r by b.
And we know the value of r, right?
Yes, sir.
And what you can realize that the time period has nothing to do with the what?
The velocity.
The velocity, which means the bigger the velocity, bigger the radius, and time will be same. Small velocity, small radius, same time. It means
Yes, sir.
whether someone is moving in a small path or bigger path, if they have same charge and same mass, so both will take the same time, right?
Yes, sir.
Okay. Now we know that frequency is defined as inverse of time period, right?
Yes, sir.
And the most important thing is called the angular velocity. So what will be the angular velocity? Omega equals to, or you can say angular frequency. And that will become QB by M. And so you can say the angular displacement okay. So the theta is equals to omega t, and this is equals to QB by M into T. So if you are only interested in knowing that how much time it will take to go from here to here, okay. If this is t equals to 0 and if this is t, then this is theta. So we can simply say given a theta, we can find t as theta by omega, and omega we know is QB by. So it's like theta m by QB. So you can insert any theta, you will get any time period that will take to turn actually. Understood?
Yes, sir. Sir, can I just come back in a minute?
Yeah, sure. Yeah.
Yes, sir.
So now you can see a question. There are two charge particles. One is plus q and mass is m. Other is minus q and mass is again. So charge and mass are same. But one is given a velocity v, another other is given a velocity 2v. What does it mean? They will have different radius, but they will have same time period, right?
Yes, sir.
So both will turn by same angle, right? After some time t. So find the relative velocity after time t, or you can simply find the magnitude of relative velocity after time t, and also find the displacement after time t. Sorry, distance between the charge particle after time t. So question is find v relative as a function of time t. Also find the separation between them. Okay, let me help you out.
Sir, getting the R relative as R into under root 1 plus 8 cos square QBT by M, sir.
Okay. So we can redo this as simple diagram like this, right?
Yes, sir.
And then draw the horizontal line, which symmetrically divides the two shape. And so one will V cross B, one will turn left, right?
Yes, sir.
And the other will turn right. So what? So this after time t, it is here. And it is here because they will turn by same angle, right? Angle remains same.
Yes, sir.
So if this is theta, this is also theta.
Yes, sir.
That we can substitute eventually at omega t in the last. But if this radius is r, this will be 2r, right? Because velocity
Yes,
is twice. So if you choose the proper coordinate system, let's say this is x and this is y, that's easy for you.
yes, sir.
Then you can write the coordinates of each term one by one. Here this is easy because the separation is this much, right? I think this will not be easy to find. Okay. So we know like
Sir,
what we
if
know.
we make a trapezium out of it, we can find R
Yeah,
relative.
yeah, we can find from here actually. This you can find, right? Using
Yes, sir.
Pythagoras.
Yes, sir.
So r sin theta, this is 2r sin theta, so this is r sin theta, right?
Yes, sir.
But what is this value? So this, if I say x,
Sir,
we
it
can
will
say
be 3R minus
correct. Very good.
3R, sir. 3R into 1 minus sign.
3r minus 3r cos theta, right?
Oh, sorry, cos theta. Yes, sir.
So we got L and the height is r sin theta, right?
Yes, sir.
So the S will be under root of 3r 1 minus cos theta whole square plus r sin theta whole square. Correct?
Yes, sir.
We can take r square, that is r common, r is outside. Now what we have is 9 1 plus cos square theta plus sorry minus 2 cos theta plus sin square theta. So that will become 9 plus 1, which is 10. 10 plus 8 cos square theta minus 2 cos theta, right? That's answer. And theta equals to omega t. That's it. Correct? This is the answer.
Yes, sir.
Okay. The next part is relative velocity. So I think that part is easy, right? Because the velocity will turn by theta.
Yes, sir.
So if this is the velocity for both in the beginning, so after time t, the v will be here at theta angle, and 2v will be like this at the theta angle. If both is started here, then after time t, both will turn in the opposite direction.
Yes, sir.
And the angle turned by the velocity vector is also theta only, na?
Yes, sir.
So what is the relative velocity? So V relative we can write as under root of a square plus b square minus 2b cos theta, a square minus 2ab cos 2 theta. So 5v square minus 4v square cos 2 theta. So the relative velocity turns out to be 5 sorry, v unto 5 minus, so I can write to 1 plus, I can take 4 common, 1 minus cos 2 theta. Can we write like this? So V relative turns out to be V into 1 plus 8 sin square theta, right?
Yes, sir.
You understood this part?
Yes.
Okay. So we have two charged particles. Okay, in the previous question, we have to ignore the electrostatic interaction. So that is like explicit, implicitly said.
Yes.
So we have two charged particles. One is plus, so both have been given the same velocity, same speed, not velocity, same speed in the opposite direction. So they have different velocity but same speed. And D is the separation. Again, ignoring the electrostatic interaction, question is find the maximum velocity such that they do not collide.
So
Yeah.
QB by 2m.
How much?
Sir, QB by 2m.
QB by 2m. But QBD, na? QBD.
QBD by 2m. Yes, sir.
Yeah, that's correct. So the radius will be D by 2, right?
Yes, sir.
So this is MV by. So V is QBD by 2m. That's correct. Okay. So the next question is now if V is 2V max, which we got it here, find the time after which they will collide.
Sir, I'm not able to eliminate the theta.
Theta is something which you can find using geometry. Because if the velocity has been doubled, so earlier the radius was d by 2, now the new radius is d. Okay.
Yes, sir.
So I mean, of course, this diagram will not fit here. So what I'll do draw separately. So you can draw something like this. And then imagine this is d. So earlier the radius was d by 2, correct?
Yes, sir.
So you can see that it is going to intersect at this point, right?
Yes, sir.
And if you draw all the radius and all, this is theta, right?
Yes, sir.
And the new radius will be how much? D.
Yes.
And this is d by 2, right? Because they will meet at the line of symmetry only, right? Always. So d sine theta is d by 2,
Yes, sir.
isn't it?
Yes, sir.
So d sine theta is d by 2. So sine theta is d 1 by 2. So we can add theta equals to how much?
32.
Pi by 6. So the time after which they will collide is omega t, and t is pi by 6 omega. I hope this is clear.
Yes, sir.
Okay. So this is the when the velocity is doubled. Now, whenever you double the velocity in a uniform transverse field, your radius will just become double because m is r is proportional to v value. Okay, for one single charge particle. So getting a time period frequency and all. Okay. And once they will collide, because one is positive and other is negative, they will neutralize each other. So once they will collide, after collision, it will move like this as a single neutral particle, isn't it? Because the horizontal component will cancel out, the vertical will add up, and not add up, it will just go like this with the velocity which they have gained actually. So you may conserve the momentum in the upward direction, not conservation, sorry, simply it will continue with the same velocity. Okay, anyway, so we can go to the next concept. Now the field is uniform and transverse, but it is not semi-infinite. So now imagine here the charge particle enters like this. With velocity, we charges q mass is m. So if you enter at right angle, what will happen? You will traverse the circular path and you will come out of this medium, this magnetic field again at the same angle with the boundary, right? So the angle with which you enter is the angle with which you exit, because the circle here will be, first of all, you need to understand that if this is the velocity, what will be the direction of center? I mean, position of center. So we know that if you draw a perpendicular to the velocity vector, it will pass through the center. So we can say center must be on this line, the horizontal line itself, isn't it? Center must be on this line, isn't it?
Yes.
And because it is a right angle, velocity and center joining this right angle, the shape will be semicircle, isn't it?
Yes, sir.
Only the upper portion, the lower portion I will remove it. So whatever angle you enter with, you exit from the same, and this line will become as a the diameter of the circle. So the time for which you remained inside the field was the pi angle. So tell me, what is the time period for which it was in the medium? It was in the field actually. For what duration the particle was in field? That's called the magnetic time of flight. So what is the magnetic time of flight? So we can simply say the angle for which it was there, theta equals to omega t. Omega we know. So the t is pi by omega. Omega radius all remains same, right? Because the formula for radius of curvature is same. R equals to. See, it really doesn't matter whether you complete the circle or not. R is fixed. Okay.
Yes, sir.
So we got the radius, we got the time period. Omega is qb by 2m. Qb by m, sorry, not 2m. Qb by m. Now the question is, what is the value of momentum change?
Sir, 2 MV.
It is 2 mv, right?
Yes.
So the magnetic field has changed the momentum by this value. So what is the average force by the magnetic force, I mean magnetic field on the charge particle?
Sir, changing momentum by the time at which it is there. inside
Yeah,
the
the magnetic time of flight, right? So
yes.
so the answer is how much? 2 mv by how much? Pi
5 m by q.
by omega. So pi m by qb.
Yes, sir.
And this is really nice answer. It's 2 by pi qvb, which is the formula, right? Qvb.
Yes,
So qvb is the instantaneous force, the force at any instant. This is the average force, and it is 2 by pi of qvb value.
yes, sir.
Okay. So similarly, what happens if the charge particle will enter like this? So now the center will be where? Can you guess the center location?
So it will be outside.
Like this.
Yes, sir.
And if you write the V cross B, it will be on the left side, right?
Oh, okay, yes,
So center will be somewhere here. It is
yes,
like, it will enter like this.
yes, sir.
And so it will exit like this also. Okay. So if you enter at a given angle, say the angle is given to you as theta, you can find the angle, right?
So the other side will also be theta.
So you have to do the same thing. Find the average, find the momentum change, find the average force, find the time period for which it was in the field, which is called the magnetic time of flight. So do it for the same thing. Do it here
Yes.
on this side. I'll do it on the side. You can tell me the answer. So R will be same. MV by QB, right?
Yes.
And now we have to find the angle
Yes,
part. This is how much?
sir, sir.
This is
Uh,
2 theta.
yes,
So the angle for which you were in the field was this angle, na? 2 pi minus 2 theta. So time will be how much? Theta by omega. So what is the, okay, we got the time of flight. So now next is what is the change in momentum?
and we sine theta.
So the average force will be
By delta t.
It is QVB sine theta by pi minus theta, right?
Yes, sir.
And the last is if you enter like this. So which this is I'm leaving as a exercise. You can do it at home. So if it enters like this, then what will happen? So that you can discuss. Okay.
Yes.
The next is in the same scenario. What if the field is having the finiteness, which means if the field is confined between the two boundaries. So field is everywhere, but it is between the two boundaries. So it's called finite field. And the charge particle enters at some angle. So for find the time period, and there are many things. So it will move like this. But I can draw a circle. So it will enter the field, will bend a bit, and then once it will leave the field, it will go straight further. Okay, that is the path. So if I extend these two lines, and if I bring it backward, then this angle is called deviation suffered by the particle. This is called deviation. And this is the arc that it will travel. So this is the angle, and this angle from geometry will be equal to deviation, right? And what they give is the separation. Okay, so can you find the delta? Because velocity is given. So find delta, find radius delta, and I think that is sufficient. Then you can find everything else. So O A, so find AP. What is AP? What is O is? Okay, fine. So AP is called lateral shift.
Can you just come back in a minute?
Yeah, sure.
Sir,
Yes, you're there. Okay.
sir, yes, sir. Sir, is D also given?
Yeah, D is given.
Okay, sir. Sir, I'm getting the angle of deviation in sine inverse form. Is it?
Correct.
Okay, sir. Sir, that means sine inverse dqb by m. Yes,
Correct. Correct. So it's a, you can write in terms of R only as of now. So so you may find that day, I mean, this is called the lateral shift.
yes, sir.
So the lateral shift we can write as
R
R
into 1.
minus cos. Okay. If the D is very small, then delta is also going to be very small. So if D is much less than R, then we can simply write deviation equals to D by R. The sine of angle is angle itself, right?
Yes, sir.
And the lateral shift comes
Sir, it will be R delta square by 2.
correct. So the lateral shift you write as D square by 2R.
Yes, sir.
Okay. So these are the questions that will come across from the transverse field.
Yes.
The next is so this is like a it will act as like a Snell's law, you know, it's like bending small. If I make it really small, then we can find the deviation also very easily. Okay. And okay, let's do something. Just a moment. Now imagine if you have a magnetic field which is like a circular region. So field is here inside. Okay. So now a charged particle enters the field, and what is given to us is the radius of the region is A. Find deviation.
So,
Yes.
sir, if sir, like this charge as a whole, it will be like performing a circular path, sir. So
Yeah.
if at one of the intersecting points of the tangents are normal limits, at the other point, at any case, it will be normal.
Imagine this circle.
Yes, sir.
So it will enter like this. Okay.
Yes, sir.
And will exit this. Okay. I can make it even bigger. Okay. This is better. So this is the deviation, right? Let's call it
Okay,
theta.
okay, okay, okay. Yes, sir.
Got it?
Yes, sir.
Now you want to try again?
Yes, sir.
Okay, go ahead.
So, sir,
Yes, yes. Tell me.
so now I'm getting theta is equal to 2 tan inverse QAB by M.
I think that is correct. So the center will be somewhere here, right?
Yes, sir.
So we can draw a perpendicular to this point. And yeah, you can apply the geometry for sure. So this is theta, so this will be 90, this is 90. This is 180 minus theta, so this is theta, right? This entire angle is theta. So it is bisected theta by 2 and theta by 2. And I think that is sufficient. So tan theta by 2 equals to A by R, right?
Yes, sir.
So we got theta equals to 2 tan inverse A by R. This is the answer, right?
Yes, sir.
Okay, very good. Okay, so we finished the one part of it. One part is like when the field is uniform and transverse, then whatever is possible, we have done it. Now next lecture will be when the field is uniform but when the field is transverse but non-uniform. So we'll see all the other variety in the next lecture. In next lecture, we will be able to finish almost all motion part, and then I think one or maximum 2 lecture will take to finish the chapter. Okay.
Okay, sir.
All right. See you in the next lecture. Bye. Take care.
Bye, sir. Thank you, sir.